This is section 1.5, which deals with solution sets of linear systems. We're first going to start with homogeneous linear systems. A homogeneous linear system is the following. First, we have the matrix equation. It's AX equal to B. But notice that B is equal to 0. That is what homogeneous is. If B is non-zero, we call this non-homogeneous. This linear system always is consistent. The reason is because x equal to 0 is always a solution. This solution x equal to 0 is sometimes referred as the trivial solution. Right? Again, it is always a solution to x equal to 0, and you can see that because if we substitute 0 in for x, then certainly a times the vector 0 should be equal to the 0 vector. So the question we need to ask ourselves when we're dealing with homogeneous systems, again, the homogeneous linear system is a times x equal to 0, is not whether it has a solution, but whether or not the solution it has is unique. That means x equal to 0 is the only solution. Or whether or not there are infinitely many solutions. If there are infinitely many solutions, we call these solutions non-trivial solutions. So if you recall, x equal to 0 is the trivial solution. If you have infinitely many solutions, we call those non-trivial solutions. Let's start with the following non-homogeneous linear system. And we're going to try to determine whether or not there are non-trivial solutions for this linear system. Again, we're trying to show whether or not there are infinitely many solutions or only one solution. So let's set up the augmented matrix for the linear system and put it into row echelon form. So now we've placed the matrix in row echelon form, and we can identify the location of the pivots. In this case, there's only one. And we see that the second column is a non-pivot column, which tells us that x2 is a free variable. Hence, we know that this linear system has non-trivial solutions. And it has non-trivial solutions because there's a free variable. So I'd like to bring your attention to one thing, and that is, notice that when we perform row operations on this matrix, that the constant column does not change because it has zeros. So no matter what elementary row operations we perform on this matrix, this column of zeros will always be 0. Hence, when we're dealing with homogeneous linear systems, we can deal only with the coefficient matrix, and I'll show you how we do that on the next slide. So here you see I have written the coefficient matrix for the linear system. And now I'm just going to perform row operations on the coefficient matrix, as you see here. All I'm looking for in this case is whether or not this matrix has a pivot in every column, or whether or not it has a non-pivot column. If it has a non-pivot column, as we see here, then we know that the linear system has non-trivial solutions because it has free variables. If it doesn't have a non-pivot column, then we know that the linear system only has the trivial solution. So again, we don't have to deal with the entire augmented matrix because the constant column for this case will always be a column of zeros. Now let's consider this linear system. Now the one thing that we automatically know about this linear system, again, it's homogeneous, so we know that it has a solution, either the trivial solution or there are infinitely many solutions, in which case there would be non-trivial solutions. Here we have one equation, but we have 1, 2, 3 unknowns. So we know that this is an underdetermined linear system. So automatically we know that non-trivial solutions exist. So this question doesn't really ask us whether or not we have only the trivial solution or non-trivial solutions. It says to find the solution. So let's go about figuring out how we find the solution to this homogeneous equation. For this linear system, we could again write the coefficient matrix for the linear system as I've done here, but it's really not necessary. But in its coefficient form, we see that there are two non-pivot columns, the x2 and x3 column. So all we really need to do is take the equation that we have here and solve for x1 in terms of our two free quantities, and we get the following. So again, for this linear system, we have identified two free variables, x2 and x3, and we've written x1 in terms of x2 and x3. Now we're going to see how we write the solution vector x. X contains quantities x1, x2, and x3. So the way we write the solution is first we write x1 in terms of our two free variables. So it's 3x2 minus 2x3. x2 is just x2, right? It doesn't rely on anything, so we just write x2. Similarly, x3 is simply x3. Now we're going to rewrite this by separating it into two different vectors. So we have 3x2 minus 2x3. For the second statement, notice that x2 is by itself, so we have x2 plus 0x3. And lastly, we have 0, because there's no x2 in the third row, plus x3. I'm going to continue to manipulate this vector that we have in the following way. I'm going to put together all the terms that have x2 and all the terms that have x3. So I end up with the following. I end up with the vector 3x2, x2 and 0, plus the vector minus 2x3, 0, and x3. The way I wrote the solution a moment ago is not incorrect, but I just changed it slightly. Here before I had 0, and now I've put 0x2. So notice it's really the same thing. So again, I've rewritten it in terms of these two vectors. And now I can pull out the quantity x2, or the parameters x2 and x3, and I end up with the following as the solution to the linear system. When we write a solution in this form, it's called parametric vector form. Right, so I'm trying to write it. It's not writing very well at the moment. So let's see. Parametric vector form. In parametric vector form, you write the solution as some parameters multiplied by vectors. Doesn't this look just like a linear combination? And that's exactly what it is. So we could say that the solution to this linear system is also the span of these two vectors. So let's say I call this vector A1, and I call the second vector A2. Then the solution is the span of A1 and A2. So why is that the case? Because x2 and x3 are free variables, so they can take on any values. And so this really represents a linear combination of these vectors A1 and A2. Let's now think about what the solution to this linear system looks like in a geometric context. So we have the span of two vectors, and whenever we have the span of two vectors, generally what we end up with is a plane. So I've graphed in 3 dimensions the vector 3, 1, 0. So we go 3 in the x1 direction and 1 in the x2 direction, which gives us this vector right here. And then I've graphed the vector 2, 0, 1, so it says go 2 in the x1 direction and 1 in the x2 direction, which gives us this vector here. So notice that we get a plane in R3 that goes through those two vectors. And notice that that plane contains the origin, right? So the origin is also part of the solution. So I wanted to quickly revisit the problem that we were looking at in R2. Again, this is the problem that we found had non-trivial solutions. And so what I did was represent that solution in reduced echelon form. Again, x2 is a free quantity, and now I've written x1 in terms of x2. So we can also write this solution in parametric form in the following way. So we have x is x1 and x2. x1 is 1/2 x2, and x2 is free, so we just write x2. So this gives us x2 times the vector 1/2, 1. That's, again, if we take the parameter x2 out. So this is the parametric vector form of the solution. Notice that this can be written as the span of the single vector 1/2, 1. So this is a span, again, of a single vector. Again, we have a constant times the vector, so it's all possible linear combinations of this single vector. So let's talk about what that looks like geometrically. So now I've drawn the vector 1/2, 1 in the Cartesian plane. We're in R2, so it's just the plane. And what does it mean geometrically that we have the span of this vector? Well, it's just a constant times this vector, which means that we're just looking at all multiples of this vector. If you recall, all multiples of a single vector are essentially a line that lies along the vector. So whereas the span of two vectors gives us a plane, the span of a single vector gives us all multiples of a single vector, which gives us a line. I would like for you to look at this linear system, which is slightly different from the linear system that we had previously. Again, this is a homogeneous system. And I would like for you to take the coefficient matrix and put it into row echelon form and determine whether or not this linear system has only the trivial solution or non-trivial solutions. So you should actually pause the slides at this point, because I'm going to write the solution for you in just a moment, but I want you to try it on your own. If we look at the row echelon form of the coefficient matrix for this linear system, which is given here, then we see that there is a pivot in every in every column of the coefficient matrix, which tells us that there are no free variables, which means that the only solution is going to be the trivial solution. So we automatically know that the reduced row echelon form of the matrix must be this. So the only solution, again, is the trivial solution. You must recall that the homogeneous linear system always has a solution. It's either only going to be the trivial solution, or there will be non-trivial solutions. Notice that the non-trivial solutions include the origin, so this is also part of the non-trivial solution. But it can be the only solution itself. So the graph of this solution is kind of obvious and simple, and that is that when you have the solution x equal to 0, you're just graphing a point. So the solution set for this case is simply the origin, or the point 0, 0. Let's look at a comparison of a homogeneous linear system. Oops, I just lost everything. Hold on one second. Okay, so again, once again, we are comparing the solution to the homogeneous equation to the solution of the non-homogeneous equation. So again, homogeneous simply means that the constants are zeros. For the non-homogeneous case, they're non-zeros. So one of them could be 0, but they can't both be simultaneously 0, otherwise it would be considered homogeneous. So recall for this particular example, the solution was the span of the vector 1/2, 1, which we found geometrically was this line that passed through the vector 1/2, 1 and through the origin. So now let's see what happens for the non-homogeneous case. So in this case, we have to look at the augmented matrix for the linear system. And if you do the work, you'll find that in reduced row echelon form, you get the following. It's a little messy, so let's see if we can read you that. So you get this matrix right here in the reduced row echelon form. So x2 is still free, but x1 has this little extra value here. Right? So when we write the solution for x1, it's minus 1 plus 1/2 x2. If we write that in parametric form, so x again contains the quantities x1 and x2. So here I've just put in what x1 was, which was minus 1 plus 1/2 x2. x2 is free, so we rewrite it. And now notice that we have a constant plus something multiplied by x2. So I've just separated that into two parts and then separated that into two vectors. Notice that the solution to the non-homogeneous equation looks kind of like the solution to the homogeneous equation. At least part of it is there. Remember, this span of 1/2 1 is simply some constant multiple of 1/2 1. But we have this extra part. This part is called xp, or the particular solution. And obviously this other part is simply the solution to the homogeneous equation, so we'll call that x sub h. Right? So that's the homogeneous solution, which we have over here on this side. And xp is this vector -1, 0, which we call the particular solution. To draw the solution to the non-homogeneous equation, so that's the equation over here, notice again that it has the homogeneous solution. So what you see currently drawn on the right-hand side is the solution to the homogeneous equation as we have the red line on the left-hand side. So how do I get the solution to the non-homogeneous equation? Notice that I take this graph of this line that goes through 1/2 1, and I add to it the vector -1, 0. So -1, 0 looks like this. And so what I do is I add that vector -1, 0 to every point along this line. The result of doing that is the following line. This is the homogeneous solution plus the particular solution, or the solution to the non-homogeneous equation. So the solution to the non-homogeneous equation is the same as the solution to the homogeneous equation, except it's been translated to the tip of this particular vector, right? So this actually is offset a little bit. It should be going through the tip of the particular vector. So again, the solution to the non-homogeneous equation is the solution to the homogeneous equation, which we have here, that has now been translated to the tip of this particular vector. So here's a theorem that tells us the relationship between the solution to the homogeneous equation and the non-homogeneous equation. It says if the non-homogeneous equation is consistent, right, so that non-homogeneous equation is given here, then its solution is the homogeneous solution, which that is when b is equal to 0, plus the particular solution. So this actually should say x sub p. In this solution, xh is the solution to the homogeneous linear system, which is given here, right? It's just that the b is equal to 0, and p is the particular part. Geometrically, the solution to the non-homogeneous solution is a translation of the homogeneous solution to the tip of this particular vector. So for example, if I had a plane, I would simply translate that plane away from the origin to the tip of the particular vector. The homogeneous equation or solution is always going to contain the 0 vector, so it will always pass through the origin. The non-homogeneous solution is not going to contain the origin. It's going to be translated away from the origin and pass through the tip of the particular solution.